All right, let's go with it. Chapter 3, Chapter 4, Chapter 5 is all about probability. Technically, it's almost like a different class by itself. Maybe even should be a class by itself. But we group them together. Some classes in college call this class probability and statistics because there's kind of two different pieces. So chapter 3 is going to be interesting. Chapter 4 is going to be a little more difficult, more interesting. And chapter 5 is going to be more difficult and more interesting, okay? So want to kind of get a handle on chapter 5 because chapter 5 is going to be somewhat toughy. We are going to take a test on chapters 3 and 4 only. And after that's done, we're going to take after we go through chapter 5, we're going to take a test on chapters 3, 4, and 5. Good? It's almost like we're going to take you're going to see chapters 3 and 4 twice on exams. Mr. Ajiev, why torture us? Sorry, that's the way it goes. So let's try to get a good handle on these here as we gear ourselves for the next exam. So chapter 3.1, just real quick, what is this all about? Basic concepts today. If maybe we'll get to conditional probability and the multiplication rule. And then gearing up for next time, the addition rule and then the additional topics. That's kind of chapter 3 at a glance. So let's jam. There it is. Like before, all the stuff you need to write down are going to be highlighted. At least I think should be written down, be highlighted. And if different than I'll tell you, I'll just try to highlight it myself. Okay, let's go with it here. So what in the world, some vocabulary, just like we did for chapter 1, a whole bunch of vocabulary to write down. So what is a probability event? And as we set up a probability experiment, this is what it looks like. So an action, a trial, something that we're going to do that we actually get a specific count, a measurement, a response is obtained for it. So the question is, what in the world is an outcome? The outcome is that result just for a single trial. Stuff again. All right, then we also have something called a sample space. Sample space is all the different things that could possibly happen. Wait around until I see everybody sort of done copying, and we'll keep on going. One more thing here, then something called an event. The event is what you want to happen. The outcome is the one single event. Sample space, all possibilities. And the event is the whole thing altogether. This is what I want to happen. Sorry, that's by the most amount of writing we'll do 3.1. I hope there. Okay, let's jam. Let's think this with me, and then we'll go for it, because some things you don't write down, sometimes we just kind of think about it here. So, I think I know. We have 4 different blood types as humans. We have an O, we have an A, a B, and an AB. Dogs have 13 different blood types. Is that kind of funny or what? I don't know why I know that. It's kind of weird. Okay, so, but here's the thing. For each one of those blood types, it's either a positive ribosome or a negative ribosome in it. So there's a positive charge or a negative charge for each one. Okay? So now let's do this here. Determine the number of outcomes and then identify the sample space. Let's do that first. Now, what we usually do, especially in like probabilities, we want to start off slow. We want to start off with diagrams. And then what we want to do is we want to build in the mathematics behind it. Okay, so we're kind of like, oh, that's going to be this rule, that's going to be that rule. But for starters, let's just go with it. When we deal with small amount of numbers, we like to make something called a tree diagram. A tree diagram is going to visually represent all the different types. Okay? That's cool, starting off, and then we'll get ourselves to math stuff. So, don't need to write this down, we good? But here's my little tree diagram. Tell me if you guys agree or disagree. Should look like this, is that right? So I got O, A, B, and AB. And for each one of those, I have the plus and the minus. Okay, so now real quick here, your job. Can you list for me all the different, or the sample space? Give me the sample space, which is all the different probabilities, or possibilities. Can't tell you that already. Messing up already. So give me all just the sample space for this one. If you want to put a exercise 1, that's fine, and just put blood types next to it, that's fine too. Just exercise 1, blood types. And then list for me all the different ones. Real quick here, out of curiosity, how many are there right away? 8, right? So it's kind of like there's 4 different types. Each one is 2 different types. So 4 times 2 is 8. So if you can list 8 of them, that's cool. And that's the first principle we'll get to. Something called the multiplication principle, the fundamental counting principle. All right, I like to do this slow, especially chapter 3, because if you don't get a part of it, then you're kind of lost in the math behind it. So we have to sort of work our way through these pieces here. Okay, everybody got all 8 of them down. I got 2 nods yes, and the rest are not nodding at all. So I'll wait a little longer here. All right, see what is wrong. I gave you guys the answers already. Is that right? On the bottom there? Yeah. I will definitely walk those out next time. So I'll be good there. Yeah, some of you guys are drawing the tree diagram as well. That's fine too, absolutely. Okay, but we got, let's see, if we do the O's first, so O positive, O negative, and we have A positive, A negative, B positive, B negative, and AB positive, B negative. Perfect. 8 different possibilities. It does come from this concept of if you have 4 possibilities for the first one, 2 possibilities for the next one, you multiply the possibilities together to get your sample space. That's cool. Okay, how about a simple event? Let's do this one here. This one probably should write down at least this piece here. So simple event is an event that consists of a single outcome. we're going to deal with simple events first for a little while, just to sort of get the hang of it. And then we'll go into non-simple events, which gets a little tricky. The simple events is just consisting of a single outcome. You want this and this. So on the blood test that we had before, that would be like O positive. Right? That's a simple event. This one, let's talk about this one. You're tossing heads and then rolling a 3. Is that a simple event? Yeah, it's one single possible outcome out of all those. Rolling ahead, it goes to the first one right here. Tossing a 3 would be right here, so we would label it as H3. Okay, contrast real quick here. What is a non-simple event? Something that looks like this. So event consisting more than a single outcome, here it is, tossing heads, so that's good. But then rolling an even number. So now we have this possibility, and this possibility. So no longer a simple event. Now we got to think about what's the math behind it. This one's easy enough, right? That's like 3, right? 3 are the different possibilities. There's 3 different possibilities here. As we get bigger numbers, as we get into more complicated stuff, we need the math behind it. So how do we label it? First of all, we just say A, if that's the event we want, equals, and then we can label this right here. So H3 would be the answer. For this one, not a simple event. We have 3 different possibilities of it happening. Okay, don't need to write down the next one. Let's think about it here. Work with me. Determine the number of outcomes in each event, then decide whether it's a simple or not. So quality control. You randomly select a machine part for a batch that has been manufactured that day. And then, so it's a factory job. What you do is you randomly select a machine part or a bolt or whatever, right? Boom, and then your job is to figure out after you do that, is this an effective part or not? Simple event, not simple event. What do you guys say? Yes or no? How about raise your hand for yes? See if you guys are awake. Raise your hand for no. See if you guys are not awake. No, it's lunchtime, right? You've got to do this. Okay, this one would be just a simple event, right? It's one thing, right? You selected one object and you look at it and you say, hey, is it defective or not? But notice you selected one piece, just one time. Good. They do this quality control in manufacturing. They do it quite a bit. What they'll do is let's say you produced 40,000, I don't know, bolts that day, right? What they'll do is they'll pick out, let's say 40 or 50 of them. And what they'll do is they'll actually measure the thread line to make sure it's within reason. So that's kind of what they do for product. This one, you just got one. Select a. Okay, let's jam on next one. Let's see if we're going to wake up this one. You roll a 6-sided die. The event B is rolling at least a 4. Simple event or not a simple event? Thank you, Giselle. Not a simple event. That because there's 3 different possibilities, right? You roll 4, 5, or 6. So not a simple event in this case. Okay, next slide. Got to write down this one here. So the fundamental counting principle. This is the basic thing we talked about. We already talked about it here. So one event occurs n different ways. The second event occurs some other different ways called n. The number of ways that 2 events can occur, we just multiply them. So blood types, there was 4 possibilities for the blood type. Each one was a positive or negative, so therefore 8 different possibilities. So eventually we don't want to draw tree diagrams all the time. That would be crazy. It's more complicated now. All right, let's see. Anybody dare? Can you guys think of another example where the fundamental counting principle could be developed? one unit goes one way, another one the other. With the sample space, we multiply the number of ways the first event can occur, or the outcome can occur, the number of ways the second outcome occurs. All right, now the question is this: what happens if there's 3 events? Does this thing kind of just keeps on multiplying into it? Absolutely. So don't need to write this down, but this guy can be extended for all the different events occurring, right? So if we added for the blood types, if we had the 4 different blood types, and then we put in positive or negative, and then we also put gender inside it, right? That just double it. Now we have 16 on our hands. So we just multiply the possibilities to that. Okay, don't need to write down the next one, but let's talk about it. Let's see if we get to the answer here. So here it is. Purchasing a new car. Possibilities are a new manufacturer. Now, real quick here. Sometimes probabilities are dumb because there's no way you're going to walk in like, you know what? I don't care what manufacturer. I don't care the right size or the color. Heck yeah, we care about color when we buy a car, right? Or manufacturer, or what kind of car you want. But let's just say, so at this point, what are the different possibilities? Anybody? I don't think so. So what are the different possibilities? You can select one manufacturer, one car size, and one color. Yes.
27.
27? Talk to me here. Everybody agree with 27 or no? Or how did you come up with 27?
Wait. I changed my mind. 24.
24. I think 24 is getting at is this right here. How many possibilities for the first column? 3. How many for the second column? 2. That 3 times 2? 6. So there's 6 possibilities if this was over here. Then how many different possibilities for color? 4. So 6 times 4, 24. So in this case, there's 24 different options we got here. It's the counting principle, right? Possibilities for the first column, possibilities for the next column, and then possibilities for the third column, and just multiply them together. So here's the answer on this guy. Here's a diagram. Don't need to write it down. This is just for us to consider, but here it is, right? 3 different manufacturers, 2 different sizes, and 4 different colors mixed 24 different ways. Is that good? You guys good? Okay, Jam, let's go with this one here. Let's go to code. Anybody have a code that involves 4 digits? Oh, our PIN codes, right? On our bank account statements, right? Usually our bank cards, right? They're usually 4 codes here. So how about this here? Access code. If you want to write this one down, that's fine. If you don't, just kind of think with me. It's kind of whatever your learning style is here. Access code for car security system. Ooh, anybody have a car security system that has 4 different things to do on it? No. I'm not that advanced either. Okay. Okay, so the arrangement is from 0 to 9. How many access codes are possible when each digit can only be used once and not repeated? Oh, wow, that's cool. Okay, hold on. Let's talk about this here. Each digit can be used only once, can't be repeated. So real quick here, out of curiosity, how many different possibilities to put in for the first digit? 10, right? You get 0, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Now, let's say I picked a 4 over here, right? 4 cannot be used anymore, right? How many possibilities for the second one? I only have 9 choices left, is that right? So once I put like, I don't know, like 8 in here, right? So now how many possibilities for this one? 8. Let's say I put a 1 in here. How many possibilities for this one? 7. Okay, I think we got it. Look cool like that. Okay, because the digits can only be used once, the choices are 10 for the first one, 9 for the next one, 8 for the next one, and 7 for the last one, or, okay, there it is. 10, 9, 8, 7 makes 5,040 different combinations. Is that, now the question is that a pretty secure locking system? Yeah, in fact, our PIN codes, once you use it 3 times wrong, right? ATM shuts you out, right? So you have, and then real quick here, on your bank cards, are we allowed to repeat numbers? Yes or no? Yeah, we are. Okay, so that, actually that's more like number 2. Here it is. Here's number 2. Because each digit can be repeated. So how many possible combinations for the first choice? 10. Good, I'll help you. How many different possibilities for the second choice? Still 10, right? Because I could use the number over again, right? Third choice? Fourth choice? What is 10 times 10 times 10 times 10? 10,000 is perfect. Oh, this is so cool. Hold on, real quick here. Let's go back real quick. So if I can repeat the same number over and over again, I'll have 10,000 choices. Notice without the repeat, I go down to 5,000 choices, right? That extra little repeat or not repeat option just doubled, practically doubled my optional choice or my sample space. Good. Okay, let's jam to this. You guys tell me here, this is for you guys. Each digit can be repeated, but the first digit cannot be 0 and it cannot be 1. And I think that's the way most banks work right there. It could be a 1. So all yours, go for it. Among yourselves, talk among yourselves. This is like you do it and talk to someone next to you kind of close and say, hey, I think my number is this. Look it up your calculator. You may want to have to multiply these guys together real quickly here just to sort of see. So I want to know the sample space. Each digit can be repeated. First digit can't be a 0 and it can't be a 1. And anybody got the answer without a calculator? The only other thing is, anybody get an answer without a calculator? All right, shout out if you got it. If you're right. Before it says 8,000, tell me if you guys agree or maybe get a different number. Kimberly says yes, 8,000 it is.
8,000.
Awesome. Okay, I got 3 8,000. I'm gonna go for it here. So possibilities are, here's where we jump to this one right here. So the first choice, you only have 8 choices, right?
Yes.
Because you got to get rid of the 0, get rid of the 1. But the other ones are all 10s. So 10 times 10 times 10 with that little 8 at the ends, 8,000. Could you have done it without a calculator? Yes, you could have done it. Okay. There it is. It's the fundamental counting principle. There it is for probability. Next. Now let's go into something called theoretical, or the way we normally do probability. And we'll deal a little bit of time with this one. Okay, so the way we say classical, or the way we say theoretical, is the fact that we are not looking at a physical object. We are thinking about all the likelihood, if it's not a yeah, you can almost say in theory, if you have a coin, here's the different options, right? If you have a dice, here are the different options. Now we understand with dice particularly, you can actually weigh a die a certain way that it'll come out, the numbers will come out different. So that's the issue there. We're not rolling dice. I'm trying to figure out the possibilities here. So what we do in the classical model, or the theoretical model, is that we just We just assume that each option is as likely as any other option. Okay, formula. Got to write this one down. So P stands for probability. The E is what you want to happen. So it's going to be like P of 6 if you're trying to roll a 6. It's going to be P of 7 if you're trying to roll a 7. Just kidding, can't roll 7 in dice. Okay, so notice it's the number of outcomes for event E to happen. And on the bottom, it's the number of outcomes in the sample space itself. So what are all the different options? Okay, let's do something together. Again, tell me if I'm way too fast. Let's slow down. Got to see a couple of people still writing, so please tell me. Slow down here. Write the next step down if you like, or let's do it together. But here it is. We're going to find the probability of this happening here. So you roll a 6-sided die. Find the probability of each of these events happening. So again, shout out the answer if you got them. I'll just give you the sample space first here, real quick here. I think everybody has played with dice before, hopefully. So the possibilities or the sample space are 1, 2, 3, 4, 5, or 6. We got some funky dice too. That's a 6-sided die, right? Have you guys ever played with a dice that's more than 6? Can't really. What do you say?
Yes.
Yes. How many sides?
I think it's 12.
How many?
12?
12, yeah.
The math class we did. I don't remember this, but we did.
That's cool. Okay, yeah, 12-sided die. There's, I think there's a 10-sided die as well. Not just only 6, but this time there's 6. Okay, GM, you guys tell me here. Shout it out. The answer if you got it. Give me the probability. This is a number, right? It's a fraction usually, or a decimal. Give me the probability of rolling a 3. 1, 6. I could probably go with that. So probability of rolling a 3 would be. Now you can't. If you want to, don't write rolling a 3. If you want, you could just say P and then put the 3 inside there, right? Because we kind of know what we want, right? P3 or P of 3 would be 1/6. And if you want to, decimal approximation is fine, or a fraction. If things get really complicated, we can just go to decimal approximations. But normally, for easy stuff, we write a fraction. Okay, rolling a 7. Thank you. It's not possible. There's no 7 on a 6-sided die, so the possibility of that event happening is 0 on top. You still put the 6 on the bottom to set up the computation, right? But it's 0/6, which is just 0 anyways. Okay, guys, we good there? Down. Okay, and then rolling a number less than 5. So this is where our C value comes in. So if you want to, you can sort of think to yourself, okay, what are the different possibilities for that to happen to be true, right? So I roll a 1, I roll a 2, I roll a 3, or a 4, that would happen. And answer anybody. 4/6, perfect. And then what we do is we always reduce it. So even though it doesn't say it on the slide here, I should change it. Usually we'd write it as 2/3. So 4/6 is the first we write down. We reduce that fraction down to 2/3. And as a decimal, 0.667. Okay, guys, does that make sense? This is classical probabilities. We're just thinking of different outcomes. We assume all outcomes are likely. Now let's go on to something a little bit different. Let's go to something like this. It's called empirical or statistical probability. So now we're actually observing things. based upon observations, we look at stuff happening. And what we want to do is we want to look at something called the relative frequency. I think we've heard that word before, right? Relative frequency of an event. How likely is that to happen in comparison to others? P of E, notice it's the same formula. The E's in there because it's just probability of the event. Probability of event E happening. Total probability, or the summation of all the frequencies added together. Good to go. So total frequency, how many altogether versus how many of the things you want out. All right, let's jam. Again, don't need to write this down. Let's kind of think with it together here. So company is conducting an online survey. So this is a company wants to know selected U.S. adults to determine how they read books during the past year. We have 1,490 adults have been surveyed, and the pie chart shows the results. Here it is. Note that digital books include ebooks as well as audiobooks. So a person listening to it or some kind of digital device to read their books. What's the probability that the next adult surveyed read only printed books during the last year? Okay, this is Pew Research. It is by far the biggest research company in the United States. They do also international studies as well. So they're pretty much top of line research for anything. They do some pretty good work. So this is 2006 studies. So here it is. Let's see. Anybody? Oh yeah, 1,490 people. 395 of them said I didn't read a single book. Yeah. The other one said read only printed books. So it's just that flipping the pages kind of thing just has to be there. Read only the digital books, that's it. And then read both digital print. Out of curiosity, just total curiosity. How many, let's do the survey for the class itself, and then go back here. Just kind of think to yourself, just last year. Last year, I'm gonna go with, so either read only printed books, not including your textbooks, not those, but just for pleasure. You only read digital books, that's it, because you have one phone or a tablet. You read both printed and digital, doesn't matter, or you just not read a book at all last year. So think back to last year, 2019. Just a quick show of hands here. So how many read only books in print for pleasure? If you have a stash, you go there. Good, bookshelf. Okay, cool. Read only digital books. Man, I'm in the information age. I have a tablet. I read all my books on a tablet. Cool. Okay. How many read both print and digital? Doesn't matter to you. I go both ways on that. It's fine. Cool. And then read no book last year at all. Nothing was interesting. Okay. That's cool. Okay. I'm thinking like, that was, I think in this class, we actually had more the digital book readers by average rather than that. Okay, so let's jam. Let's jam with this. Thank you guys so much. I always do the thing about who's for the death penalty, who's against, and we'll get to that one too. That's an interesting thing. That's changed over time. All right, no, the responses are not equally likely to occur, right? Not all the responses, not like the rolling a dice, right? This is not the same as rolling a dice. You actually cannot have a classical probability formula here. It doesn't work because each time the survey is going to be done, it will be slightly different. And it's not just the same likelihood to occur. So we have, if you want to count up all the ends, right? Even though we already said it, right? We have 1,490 people surveyed. We're good. So with that, you guys give me the empirical probability that the next adult surveyed would say, I read only printed books. I only read printed books. So let me look here. Probability. All right, so let's go with it, see if we agree on this one here. So I would do this. It's going to be 517 over the 1,490, and the answer is yes, perfect. Okay, so the question is, Mr. Ng, how far do we go out? Is it just 3.4? Is it 0.38 or 0.39? Is it 0.388? Don't know. It just depends how precise the study wants to be. We're good. And then the question is, do you need this number to do another calculation? If you need to do another calculation, then you want to use a little bit more precise numbers. But if you have 0.39, that's perfect on an exam, right? If I say maybe like 2 decimal places, that'd be kind of at least a little fun. Okay, one more. Let's go one more here just to get it. All yours go from beginning to end here. Companies conducting a phone survey of randomly selected individuals. It is determined the ages of social networking site users. So do you use Facebook? Twitter. So far, 975 social networking site users have been surveyed. Okay. The frequency distribution shows the results. Okay, what's the probability the next user is surveyed is 23 to 35 years old? Anybody with a possible answer? I don't know the answer either, so I'm gonna look it up. Everybody okay there? 312 is what we are looking for. This one up here, and then 312 is the second row down. And the total rent total, there it is. 2.32, good. Anybody else need to do that themselves just to make sure? Okay, one more probability. I'm gonna flip the slides here. Real quick. Let me flip the slides. I don't have to wait for it. Okay, one more different probability right here. This one right here. It's called the subjective probability. What? Seriously, there's something called guessing? It should be at least educated guessing. That's kind of based upon, usually based upon experience of the person. Kind of gives you at least a, like he's dealt with these numbers before. And the rule of thumb in grading is usually about A's are going to be the top 10% in the class. That's the person that sort of should get the A. Does it always work out that way? No. That's it. Okay, so it's intuition. It's educated guesses. And then it's just an estimate. I think about 50%. Hopefully more than that, guys. Hopefully more than 50% of you guys passed. So here's just a quick example. There it is, a doctor. Doctor feels like this patient has about 90% chance of recovering. Oh, it's a doctor. He's dealt with this before. Hopefully goes from there. Okay, so these three right here. Boom, boom, boom. Let's go just real quick here. Let's go. The homework questions are going to ask you to do this here. They're going to ask you to classify the probability. So as you read this, just real quick, don't need to write it down. Just kind of think with me real quick here. So classify the example below as classical probability, empirical probability, or just subjective probability. Okay. So boom, the probability that you'll get an A on your next test is 90%. Anybody, shout out. With the studying for it, right? You did the study guide. You went back to your homework. You did the question like, man, I'm going to get about 90. Like, for me to get an A, I think I've probably about 90% getting an A. Starts with an S. It's subjective, right? You have no real data, right? You're not looking at any data. There's data in front of you, right? So then it's kind of like on your own, or based upon also what you did on a previous test, or how you really understand the information this time around. Okay, subjective, yes. It's just your educated guess, okay? Again, don't need to write it down. It's going to think with me. Probability that a voter chosen at random will be younger than 35 years old is 0.3. Anybody? Empirical, that's right. There's no defined sample space here, right? There's just going to be a number of registered voters, right? However many there are. And are you talking about a city, county, talking about state? What are you talking about, right? That's going to be depending on that. So, empirical. Probability of winning a 1,000 ticket raffle is 1 out of 1,000. Has to be classical, right? Yeah, you know how many outcomes there are. There's 1,000. You bought one raffle ticket. Your likelihood is 1 out of 1,000. Okay, before we go on to the next step, just real quick here, write this one down. You'll see on the homework here. This whole concept of this only works when we have large numbers. And so now this is kind of like the connection between the empirical and the theoretical. And if it doesn't, I mean, there's something wrong. So if I was to bring a die into class and we just started rolling the die to get a 3, right? We should kind of see that 1/6 of the time we're rolling that 3. If we rolled it 10 times, for some reason we get 4 3s in a row. Does that mean that our theoretical one is wrong? No, it just means we may have to roll this 1,000 times to get close to that 1/6 option. Law of large numbers means that you're going to be about at the theoretical level as long as experiment has been repeated over and over and over. Here. Good. Now let's talk about things happening or not happening. So here's our very rough estimation of things here. So range of possibilities rule is something that's probable, sorry, something's possible. That's different. So first things first, a probability of an event E is between 0 and 1. If I'm going to write it down in math terms, it's like this right here. So 0 is the not probable at all. So 0 is less than or equal to P of E. Have you guys seen that in algebra class before? Where like the X is kind of stuck in the middle. You have one number on one side, one on the other. No. No. Okay. Close your eyes during that lesson, okay? So probabilities are always between 0 and 1. That's the first step. Second step is this is the way we normally think about them right here. So if something is impossible, it has a probability of 0. That's the only time you can say like that's impossible. If you're at a quarter, it's unlikely. 50.5, 50%. Again, it's 50-50, so you have an even chance for either way. Our cutoff normally is 75. If you're above 75, you are likely to happen. And 1 just means that it has to happen. Some math stuff here just a bit. Okay, and then some math things here, just to keep in mind here, some math formulas, and something called the complement. Sorry guys, I see about 3 people still writing, go for it. One more page of writing here, just a second. Okay. The complement. Let's talk about this right here. Very important to grasp. Complement or complementary events just means events that can happen because something else has happened. So sometimes designated as E prime. So denoted E with a little almost like apostrophe. No apostrophe afterwards. We say E prime. We say complement of E or we say E prime. But here's, let me kind of write down all of them here. We'll talk about the math behind them in just a bit. So complement means E is not happening. And what we do is there's kind of 3 different math formulas that come out of it. So if you're saying rolling a die or rolling a 3 on a dice, probability is 1/6, right? So which goes write stuff down first. Go for it. Write it down first before I start going on. talk about this one. I think this needs a little bit of a conversation. So talk to me about this here. Let's talk about in terms of rolling a die. Rolling, give me this right here. What's the probability of rolling a 3? One six, there we go there. 1 6. What's the probability of not rolling 3 of that? 5 6. There we go. 5 6. Absolutely. Okay, so real quickly here, this first term says, hey, 1 6 plus 5 6, well, that gives me 6 over 6. Or 1. Absolutely. If all the different possibilities of this happening, all the different possibilities of this not happening, better add up to 1. 1 possible. Okay. How about this one here? If I subtract 1 from here, so 1 minus 1 6, wouldn't that give me 5 6? Everything there? And vice versa. If I do this one, then 1 minus 5 6 would give me 1 6. So where are we at? This is this one here. And that's this one there. That's this one here. That's this one. Good there. So we can actually figure out probabilities by finding what could not happen instead of what can happen. So it's just an indirect approach. Bring that together. Okay, let's try it. And usually that deals with like big data. You have a whole bunch of big data, then I'm not going to calculate that. It's easier to calculate it not happening. So let's go back to not that one. This one right here. That's a good one. So find the probability. Want to write this one down. We have the information already before. So find the probability of randomly selecting a social networking site user who is not 23 to 35 years old. You guys real quick here on your notes. What's the probability of selecting a user that was? 32, I think so. Yeah, let's see. Let me go back in my notes real quickly here, see if we can find it. I'm gonna make this bigger. That's my little. Oh, love it now. Wow, I can see things now. Okay, where's our probability for that to happen? I think it's 32, right? It was this one right over here. Oh yes. Da, da, da. Okay. So all yours for this one. Can you find the probability of selecting not a 23 to 35-year-old? Shout it out when you got it. Or my mouse breaking. 2. So the probability of selecting not a 23 to 35-year-old. Let's see. This is what we had before, is that right? So then let's just subtract 1 from that, right? So subtracting 1 from that, or 1 minus 0.32. Are we okay with the 0.68? Talk to me. People are not talking to me. Are you okay with that? You just subtract from 1. That's it to get the non-probability. Okay. 2 things here. I think we'll finish off with this one here. So how about this? Probability event consisting of tossing a coin and then spinning a spinner. Spinner is equally likely, and each of those numbers. You need to, you could choose a true diagram, but let's see if we can kind of just look realistic here. So event A happening. So it is tossing a tail and spinning an odd number. Can you give me that? Event B is tossing ahead or spinning a number greater than 7. So now we got to think about how we put those two possibilities. Hey, this is not a simple probability. So let's see if we can not make a tree diagram, but can you somehow figure out some notation that will get you to listing the possibilities? That's what I want. So what letter should we use for tail? T. And then now can you list, let's see, the spinner has 8 different numbers, but I want to show an odd number. So can you list T for tail and all the odd listings? So I'm gonna go what, T1, is that right? T3, T5, T7, is that right? That's gonna be my piece there. So I have 4 different possibilities. How many possibilities in this event? What's the sample space? Before, go ahead, sorry. In total, how many different possibilities here? There's 16, is that right? Right, 8. There's 2 different possibilities for heads or tails. That's 2. And for the spinning thing, there's 8. So 2 times 8 is 16. Cool. Anybody got probability for number 1? 25%? I think so. Let's jam. So let's see if this makes sense. There's my T1, T3, T5, T7. And the probability of tossing a tail and then spinning an odd number is going to be, you got 4 different options, because I can tell, because I can list them down. Our sample space is 16, and how about 1/4 or 0.25? For probabilities, almost all the time, we don't like to deal with percents, we deal with decimals, so just 0.25. Okay, are we good there? Almost a break time here, let me go back. Okay, tossing ahead or spinning a number greater than 3. So can you list those first? Go for it. I think I'm gonna use H for head. Kind of careful here. Hold on, tossing ahead. That's one thing, right? They got this little word or now. Or means either this has happened or that has happened. So give me a tossing ahead. All the different possibilities there. Or spinning a number greater than 3. It's a tough one. Let's see. Event B occurring would be what? Looks like H1, H2, H3, all the way to AH or H8, right? Because those are all the H's, those are the head. And then we have or spinning a number greater than 3. So that can happen with the tail, right? Because we already got the head stuff done, right? The tail would be then T4, T5. Let's see if this one right here. See if this makes sense. Hopefully you guys wrote these down. So H is getting ahead up to here. So it doesn't matter what I get for the number, but as long as I get a head. All these are circled here. It says or rolling a number greater than 3. So I already got the H3, H4, H5, H6, H7, H8. So that means T4, T5, T6, T7, T8 will be the other possibilities. Okay, are we good there? All right, grand total, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Sample space again? 16, I believe, is that right? Sample space is 16?
Yes.
So 13 out of 16, or roughly 0.813. Okay, is it getting a little bit more complicated? Yeah, just a bit over here, huh? Just a bit. Good, before. So the important clue word here is this or right over there. Tossing a head or spinning a number greater than 3. So spinning a number greater than 3, we already got those right over here, right? So there was these little 4, I went to 5 pieces. We did not need a double count here. Right? Count these guys. Stop to me, some people are staring at a screen. Any questions on it or anything that you want to think through on that one?
Okay, so the H and two heads and tails, right?
Say a little louder.
The H represents the
Head, rolling the head first.
and the T is tails, right?
T is for tails.
But in the thing, it's not about.
Oh, sure. Let's go ahead and take a look. Go back on notes here and go to here. Go ahead, talk to me. Tossing a head, right?
Yes.
So once you toss a head, you don't care what the number is, right?
So the T represents what is this? The spinner.
The spin, yeah, the spinner only. Who cares about the fact it's a tail? But my spinner was a number that was greater than 3. So it was a 4, 5, 6, 7, 8.
Okay, now if we go back to H,
There's
there's 8 options there. So
Yeah, it's this one right here. Notice there's H4, right? H5, right? H6, H7, and then H8. You have these 5 options that were already counted. And because they already counted, we don't count them again.
So it wouldn't be like, after you, instead of, because there's a 50% probability of fixing. So it's like already set.
Yeah, so if I roll the H8, right? That has already been counted in my event. I don't need to count it again, or else I'll be double counting.
Because I considered the possibility of either heads or tails, and then put that together with the spin. But it's already set in stone that all of us will heads.
This was a good one to stop that, because once we get into the mathematics of these things, this little extra space, H4, H5, H6, H7, H8, are going to be a problem area for next time. Good. How do you get rid of that so you're not double counting that? So probability, very important. How do I not double count stuff? Okay, and the answer here is 13 out of 16. Okay, class, let's take a break. A long musical break. Back to class, and we're at 3.2. We're going to talk about conditional probability. Now, this one kind of scares students. It's not that scary. Just practice a lot with it. And then we got the multiplication rule. As soon as you see those tables and you're like, what are you trying to say? Like in everything in life, right? You just need a little practice with it. If you got enough practice, you're good to go. I'm reading a book called Outliers. Anybody read a book called Outliers? Okay, very fascinating book. It talks about how certain people become experts in their field. And the author, he's published other books here, but this whole concept of he was trying to figure out what makes a person expert. And as he thought about it, he figured, look, in fact, for a person to be an expert, it's a lot of practice. To be a known expert in a field takes about, I think he said 10,000 hours to be like inside your field. And that's roughly, if you did nothing else but your field only, roughly it's about 4 years. If you do not sleep, drink, sleep, but just like I'm gonna know this field. 4 or 5-ish years. So the premise of the book was if you start early and you want to do something and you consistent in your practice, you get it. Right? Yeah, I thought it was. In reality, yeah, so it's kind of like, you know, like you go to school, I've been to school. You guys go to school for 3-4 years in the field, right? But you're not in it all the time, right? You're in it for a certain amount. So then you at least get some elementary knowledge in the field. Then what happens is you jump into your field, you start actually working in that field, right? And by working, if you still have the mindset of like, hey, does this work? Does this not work? Right? It's not just like a robot, but actually thinking about what you're doing. And you perfect those skills. Like, so then yeah, it does take quite a bit of time. Yeah. 20 years in your field, then you're like, hey, I got this. I know what this process is. And so, okay, let's go for it. Conditional probability. After that, most basic rule of jam. First things first, define what in the world is conditional probability. Probability of an event happening based upon a condition or based upon the fact that something else has already happened. That's kind of what we're looking for. And it's denoted by P, that's probability, right? Open up a parenthesis, you put B. B is what you're trying to figure out. And you got this little bar line that comes down. That bar line is given that, or based upon the condition of. Yours does the easy one, it's just given. Given A already happened. Two things, it is a much shorter section than 3.1. 3.1 is a much longer section. I think we could probably do this by end of class. Okay, so I want the probability of something occurring called B if A has already happened in the process. So that's conditional probability. Don't need to write it down. Let's, oh yeah, well, here, I guess we're gonna deal with cards here. So I put this on because sometimes some people have not played with cards before. Just out of curiosity, raise your hand if you've never played with cards before. Okay, so see if you have those. That's cool. Okay, just for probability's sake, we're not gonna get on this class, okay? But just for probability, just for this section here. So cards are divided into 4 different suits, right? Anybody name the suits from top to bottom? Hearts, diamonds, those are clubs, is that right? Clubs and I forgot myself. Anybody know? Spades and spades. Okay, I'm gonna go with it. So there's 4 different suits. They go from king, queen, jack, and then it goes from 10 all the way down to 2. Good. And instead of having a 1, this is the ace card. So that's kind of what we're looking at here. Okay, so grand total 52 cards grand total. Good. What's some other stuff here? If you divide 52 by 4, you should get 13. So there should be 13 cards in a suite. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 13 in a single, oh sorry, suit. In a single suit. Okay. Anybody play cards a lot? Raise your hand if you do that. No, we're all novices. Okay, sounds good. Okay, let's go with it here. So 2 cards are selected in sequence, which means you select 1 card, right? And then you put your hand in and you get another card. And we usually call it a standard deck. So find the probability that the second card is a queen, given that the first card was already a king, right? It We pulled out the first card. It was a king. That's great. And then we're pulling out the second card. I want to know probability that's a queen. So hold on. How many cards in the whole deck? 52. We already pulled out a king. So now how many cards are left? 51. And then how many queens are left? How many queens are left? Yeah, there's still 4 queens left, right? That's all. So what we do is we say, okay, that is the case. Here it is. We got to think about this here in our minds here. So the first card was a king. It was not replaced. We didn't put it back. So we're missing a card now. That means we only have 51 cards left. That's our bottom number now. And then we still have the 4 queens that are still left. So in this case, it's 4 out of 51 or 0.078. Are we good? This was the easy problem. You good? This is not the hard problem. Let's get more complicated than this. That was just to set us up. Next one. That's what we're looking at. Let's see, finding conditional probabilities. Here's a table. Here's where students start running away from the mathematics. But let's go through this together. The table shows the results of a survey. 2,276 people on social media were asked if they ever were offended by something they saw on social media. Okay. Find the probability that a user is male. Okay. Find the probability it's you. Given that the user was offended by something on social media. So let's see if we can write this out. So first of all, again, just take some practice here, guys. Real quick here. Lots of numbers here before you. Don't get confused too much. The question is, what? We're trying to find male here, right? This is what we're trying to do. We're trying to get this category right here. And given the fact that they were already offended by something on social media. So let me go to the next slide, see if this makes sense. It's going to be this little number right here. We're good. So notice the numbers that we're getting. So kind of let's slow down here real quick here. So we're trying to figure out the male, probability it's a male, given the fact that they have been offended by social media. So there's that little yes right here, right? The total number of yeses is 1,151. So notice we're not doing the 2,276, right? We narrowed down our place here. So the total of the yeses is 1,151. The fact that it's a male is 532. We get the probability, and about a little less than half of the male have been offended. We good? So does that mean that women are a little more sensitive? I don't know. Does it mean that women are more often on social media, therefore there's more content to look through? I don't know, right? That's another question to ask. Okay, are we good there, guys? So narrow down the category first based upon the given, and then find what you need. You guys will have some homework questions on that. Fine. Let's jump to the next piece here. For independent events, and we're just trying to get to the multiplication terms. Okay. Okay, so independent event says this is something occurs, it does not affect the probability of the other thing occurring. So that's some math for you over here. As you write it down, think about what the math means over here. Now we're getting into a little bit of the math stuff, and a little bit of the notation stuff. And there's where we get lost. So there's occurrence of one event, does not affect the probability of the occurrence of the next event to happen here. So probability that B is going to happen based upon that A was given. Notice that it's still the same thing as probability of B happening without A happening in the first place. Those are independent events. Going back the other way, we're trying to figure out the probability of A, given that B has already occurred, and it doesn't affect the probability of A just by itself. So let's talk about things like that. Jam, tell me, ever done? Two people finishing up over here. Cool. Okay, let's talk about we should write this down. Sorry, forgot this one at the end here. Events that are not independent, they are going to be dependent. There's something affecting something else. Okay, let's talk about it. We got 1, 2, 3, 3 columns here. Let's jam. So decide whether the events are independent or dependent. So selecting a king from a standard deck of 32 cards, you're not going to replace it. And selecting a queen from the deck of cards. Hey, that's the same thing that would happen before, didn't we? So doing the math, because we're going to have to prove it by math. So see if this makes sense. So let's do this one, which I think we did this one before, right? Probability, we're going to get B, or the queen, given that A has already happened. And this is the problem number 1 that we just did right after break. So 4 out of 51, very good there. What's the probability of just selecting a queen by itself? You got a deck of cards? Are we okay with 4 out of 52? Good. So the question is, are these dependent or independent? If these numbers were exactly the same, these guys would be independent. But since they are not the same, that means there has been a change by doing it. Good? You changed the stack of cards, that's what you did. You just changed it to 51 instead of 52. And you've made the probability a little bit higher on the first turnaround than the second. Just slightly. Okay, how about this one? Think with me on this one. Tossing a coin and getting ahead, and then rolling a 6-sided die and obtaining a 6. Cycle events are independent or dependent by mathematics. By using math, can we decide if it's independent? So let's see. We have 2 things happening, right? We have a coin toss that's happening. We also have a dice that's being, or die that's being rolled. And so let's see if this makes sense as we go. Rolling a dice of 6. If you had a head on a coin, is that still 1 6, right? Because that one was a coin and this is a dice, so there's no correlation to each other. Mathematically speaking, if just rolling a die, 1 out of 6 is just going to be 1 out of 6. Are we good? The coin toss had nothing to do with rolling a die. As opposed to the deck of cards, there was some influence. Okay, next one, right? Click here. Dependent or dependent? Driving over 85 miles an hour, then getting into a car accident. And this, again, it's more like getting it from statistics, right? It's getting from empirical probability, right? Sorry. But driving over 85 miles per hour, yes, it does increase the chances of getting into a car accident. Those 2 are independent events somehow. Okay, are we good there? Jam, one more thing before we get to, oh yeah, this is a multiplication. Okay. All yours is a multiplication tool. So now we're looking at events that have happened in sequence. So A occurred and then also B occurred. So what we have to do, we've got to think about. So rule number one, this one right here, it works. Oh, sorry guys. Too fast. This one works all the time. This one will occur if it's a dependent event or an independent event. That's the way it works here. Getting heads and rolling 6. There's that right there. Now, one extra caveat here is this right here. If it's an independent event, if you know it's independent, then you can forget about the conditional statement of B given A, and you just multiply probability of B and probability of A. So let's use the same stuff. Let's use the deck of cards. Then we use the coin and the dice. So if you know for sure those are independent events, you can use the second equation. If you think they are dependent events, you're going to use the first equation. With those numbers. All right, let's jam. Yep, sure, go for it. Yep. You can write it down still. Absolutely. All right, so let's go with this one here. Okay, 2 cards selected. It says without replacing the first card. From a standard deck of 52 cards. Find the probability of selecting a king and then selecting a queen. So now I'm going to pass. So probability of selecting a king first. Wow, that's pretty tight, huh? Because you figure out the first grab, somehow you get the king. On the second grab, you get the queen. That's pretty small odds here. So first things first, dependent or independent? It's dependent, right? Because on the second grab that we have, things are going to change for us, huh? So let's go with it here. So in this case, selecting a queen and then king and then a queen is going to be like this. And if you want to write this down, it's going to be P of K, selecting the king. That's going to be probability of selecting the queen given that the king has been selected already. And it kind of makes sense. I think you guys tell me if that makes sense here. So 4 out of 52 to select the king. And then once that is done, now we only have 51 cards in the deck. Therefore, we have 4 kings left, 4 queens left, sorry. So 4 out of 51, multiply those together, get you 16 out of 2,652. Wow, so guys, real quick, your probability of doing that will be 0.006. Not even a 1% chance of having that done. That's super, super small possibility. Okay, we're good there? This is a dependent event, and for dependent event, this little denominator changed. Right, it's this little piece right here. Okay. A coin toss. Here it is. A coin is tossed and a die is rolled. Find the probability of tossing a head. That's one. And then rolling a die. Dependent or independent? Can't give you the answer yet. Still can't give you the answer yet. That's right. Yeah, independent, right? The die roll has nothing to do with tossing the coin in the head. So in this case, let's see if we can write this over. So here it is. So H and 6 happening at the same time. And again, if you're going to write this down, that's fine. If you just want to look at it. In this case, it's going to be probability of getting ahead. And I don't need to do the conditional probability here. I just say probability of 6. I don't have to do probability of 6 given that I rolled an H first time. So when you guys are thinking about this, you're always thinking in your head, independent or dependent. And if it's dependent, you have to adjust the next probability. Okay, what is that? 1 out of 2 and 1 out of 6 makes 1 out of 12. About an 8% chance over here. 0.83. Okay, let's go some more math. That was just to start. Let's go like numbers themselves. Let's see. So, anybody ever torn an ACL? Tristan, football player, ever did that? No. No. Okay. That's good. So let's jam. So ACL is a ligament by your knee. When you play football, quite a bit. Sometimes that happens just because bodies are crushing into each other. The probability that a successful surgery is 95%. Did you know that are failed ACL surgeries? Okay. That was interesting. Driving into work today, I was listening to news and it FDA fires. I just listen to it all the time. They have a warning sticker that just came out like 2 hours ago, 3 hours. They said that like a Pfizer Moderna vaccine, there is a potential for brain hemorrhaging, right? Like that's the whole point. Like they take the vaccine, there's a possibility of this, right? So they put on the FDA made them put it on their label.
In this survey, successful and not successful. Not successful mean that they're not able to fix it.
Correct. Yeah, it was not fixed the way it should be. So find the probability that 3 ACL surgeries are successful. This is interesting, guys. So real quick, dependent or independent? Ooh, okay, doctor does 1 surgery, right? He's successful at 95%, right? He comes in an hour later to do another surgery. Did his success rate go down or he's still at 95% for surgeries? It could be tired. It could be right after lunch, right? But no, the second surgery is still at a 95% success rate. Does that make sense? His third one comes in in the afternoon. He's still functioning at a 95% success rate, correct? So all 3 surgeries, they are independent of each other, right? Or it could not even be the same doctor, right? It could be the same hospital in this case, right? You got 3 surgeries that are being performed. What's the probability? They are independent events, right? One surgery does not affect another surgery. Because the 95% is just the orthopedic data that we know. So in this case, 3 surgeries gone successful, you have a 0.95. Because they're independent, we're going to multiply another 0.95 and another 0.95. And so if you had to have 3 ACL surgeries on your body, your success rate coming out is 0.857. Does that make sense? Right? It's the 95s multiplied together on each other. Now that's why, what do? You go to a doctor, you get a second opinion, first of all. Third opinion if you need to. You go to a doctor that's done these, You ask him, hey, what's your success rate? That would be a good question to ask, right? Before you enter into surgery. How many have you done? Are you a regular doctor that does these surgeries? Like all this good stuff here. Okay, but real quick, the whole point is you can multiply these guys together as long as they are independent. Okay, let's jam. How about this? Can you find the probability that none of the 3 ACL surgeries are successful? Ooh, that's a fun one. Hold on, I'll give you a hint though. Success rate for 3 surgeries are 0.857. What is the non-success rate of the surgeries? Something about like the complementary of E. Remember the complement of E? If you have 85.7% is successful, right? What's the probability that's not successful? What are you going to subtract from? From 1, yeah, let's do that. So if you do this here, and the weird thing is, look at this, it's not subtracting from the total, right? It's subtracting from each and every single surgery. Good. So 95% is, or 0.95 is a success rate, right? Subtract from 1, you get 0.05. Multiply times 3, 0.0001. Okay, are we good there? So it is not altogether, it is by each. There we go. And one last one here. How about this one? We're all done after this here. How about this? Find the probability that at least one of the 3 ACL surgeries is successful. Let's leave with that. You guys, can you guys calculate this one? Think about it. Talk to your neighbor if you have one. Find the probability that at least one of the 3 surgeries is successful. What would you do? I'll give you a hint. 0.95 means successful, and 0.05 means unsuccessful. And they are independent events, right? We can multiply them across. Let's see what's the other thing. So anybody tell me what you guys would multiply by? Oh yes, okay. Euphoria says 0.05. That's the unsuccessful, right? 0.05, the second unsuccessful, and 0.95, which would be the successful one. So absolutely. Well, let's look at this. The complement to the event, at least one successful in the event means none are successful, right? So here's the fun part. You guys will come back with homework questions on Tuesday, and it could be that you're going to be totally frustrated. So here it is. At least one successful means it's the exact opposite of none being successful. Is that true? Because at least one meaning successful, that means like you have 1 or maybe 2 or maybe all 3 were successful, right? You got those possibilities, right? So because of that, at least one successful means it's the complement of not being successful at all. So go back to 2. Those are all 3 surgeries not successful. Subtract that from 1 and you get yourself 0.9999 to be your. Are we good? Okay, I'm gonna let you guys try the homework. Please come with homework questions on this stuff, because that's exactly what we're gonna do next time. We're gonna, Mr. Ngia, how come I multiply by this and this and this? How come it's not this number? I'm gonna say, well, let's talk about it.